these are some ideas that I have been thinking about for the last few months. I wasn't thinking about continuations at all. I was thinking about classical linear logic and session types, and somehow happened to rediscover some well-known facts, and I wanted to build those ideas. So I'm going to tell you like a bunch of different things that I've been thinking about. If anyone wants to join me in understanding them or have ideas about how to use them, please talk to me. All right. So I will start with, so let me start just from the very basic understanding of functional programming, which is we have higher order functions and we have currying. So if you take any modern functional language, you can write curry and uncurry, and it doesn't do anything because the language itself has currying and uncurrying built in. So just as an example, if you took Haskell and wrote down the types like this, A, B to C, you can turn B arrow C, turn that to A to B to C, which returns a function, and that's currying. So products on the left become functions on the right. And uncurry is just the opposite of currying, which is you give me A to B to C, and then I can take these two arguments, A and B, and put them in a pair. And currying and uncurrying is the basis of all functional programming that we do when we take free variables and write functions, or when we produce higher order functions and pass them around, and so on. Now, I want to pose this puzzle, which is, suppose I give you a language like Haskell, and I ask you to dualize currying. So let's call it co-currying, and what should that look like? So since products were on the left, now you want sums on the right. And you had functions on the right, so they should become something on the left. What is this subtraction? So I'm just writing plus and minus. We have plus in Haskell, which is sum types, either left or right. But can you find a type for subtraction which will allow you to write these two programs, co-curry and co-uncurry? Okay. Now this is a puzzle. You can think about it on your own time, but unfortunately, if you know a little bit of category theory, you realize that there can never be a language in which you can have both currying and co-currying. So for those of you who know a little bit of category theory, it means that so the times is a left adjoint, so it preserves colimits. And if you had co-currying, the co-product becomes a right adjoint, so it preserves limits. So A times 0 is 0, which is fine when you have currying. But if you had co-currying, you have A plus 1 is 1. Okay. Now think about types of propositions. If you think of propositions in logic, A and bottom is bottom, fine. A or 1, A or 2 is true. Okay. So just Boolean logic has these if and only if statements. But these are propositions. But let's say you have types. So when you have types, if you had a Boolean type by this isomorphism, it would be 1 plus 1, but 1 plus 1 is the same as 1. So you can never have types with more than 1 point. So there's a whole collapse that happens. It can be made more precise, but this is more or less the informal idea of what goes on. So you can have logics with subtraction, but you cannot have a programming language. People have been thinking about logics with subtraction for a long time, and there are these things called subtractive logics, co-intuitionistic logics, bi-intuitionistic logics, and there's a whole series of papers written about them, both in mathematical logic and philosophical logic, and so on. There are these no-go theorems in category theory, for which I believe it's due to Joel and his PhD student from the 1960s. And they showed that if you have a Cartesian closed category and co-Cartesian co-closed in the same category, it collapses and becomes a preorder. These no-go theorems are also important if you like quantum foundations. So there are many notes by Abramsky on what should be the right way to start thinking about quantum, which is like no-go theorems in quantum correspond to these kinds of no-go theorems in logic. So in quantum, you start from a star-terminus category, but if the products are actually Cartesian products, it collapses. So all of these people started thinking about, if you want to develop anything with dualities like currying, co-currying, or subtraction, we really have to go to linear logic. And indeed, linear logic is great. And because linear logic is very successful, everyone starts thinking about these problems using linear logic. And that's good. But I want to take a step back. Let's say we did not have linear logic. I can still show you subtraction. So if you just allow me to squeeze in this double arrow, here is currying and co-currying written in Haskell. This is a real Haskell program. Okay. Looks mysterious because I haven't told you what the subtraction is. So the point of my talk is to tell you how to build subtraction. So let me tell you that step by step.
This double arrow is not the existing double arrow.
Ah, okay.
It's different.
Yeah, it's not type classes, sorry. Yeah, but yeah. Yeah, so my compromise is don't do linear logic, but give me two kinds of arrows, and then I'll show you how to do subtraction. Okay, so of course, so from the title of my talk, you know that continuations will be involved somehow. It's such an old concept, I don't know what to even say. So I took this paragraph from Reynolds wrote this amazing survey showing that continuations have been discovered and rediscovered in many ways in denotational semantics, in program transformations, and in interpreters, starting from algol to scheme and everywhere. But in general, it's something which indicates the meaning of the rest of the program, right? There are different ways of representing continuations, and it's a whole. The continuations research is a huge deal, and so many papers and everything. One of the problems with continuations is that it's very hard to think about them because you have functional programs where you cannot think about control flow, and then suddenly continuations give you control flow. And if you go search for tutorials on continuations, they talk about time travel and futures and all these kinds of things, and they're very mysterious. Okay, so this is what continuations are informally, but since I'm from Indiana, where there are many experts on continuations, and we have this amazing class C311 where undergraduates learn about continuations and continuation passing style. And here's the very basic reason why you want to use continuations. So if you have a language like Scheme, you write your first recursive program, the hello world of recursive programs, which is factorial. And you take the mathematical definition and write it like this, but then you realize it's slow because it's not tail recursive. If you call factorial with a large number, it grows the call stack and has to wait until it reaches factorial 0 and then goes up. So it's not tail recursive because the factorial is called in a position where it's waiting inside a computation. There are many ways to fix it with accumulator passing style and so on, but continuations are a universal solution to this. Generally what you do is you write a CPS transform, you transform factorial into this CPS style where it takes lambda n, but also a k, which is a continuation. And you have to be careful about how you call the continuation and stick it in the right places. It's very hard if you just stare at it like this, but when Dan Friedman teaches his continuations, he teaches this in a very principled way by looking at where programs are returning, and some people can even write Emacs macros, which will transform recursive programs into this. Yeah, and so that's the CPS version of factorial, and then you call factorial with the identity continuation, and you get a tail recursive factorial function. This is all scheme, it's untyped, but I like types. So if you like types, there is this thing called delimited continuations where you can use functions to represent continuations. So continuations of A are just A to R, where R is the result type, and every continuation has to return something. Okay, and if you take that scheme program and try to give it types, you see that int to int becomes int to r to r. Okay, so it takes the continuation for int, and then again you have to put the continuation in the right place, and the types help you understand where exactly the results are being used. So okay, this is still complicated, and the next step is to think about the continuation monad. So int to r, that's usually how you do CPS. So that common pattern is a to r, and that gives you the continuation monad. If you are in Haskell, Haskell has very good support for monads, so you can define this monad, and it has a return and a bind, and it's very easy to implement it. Once you have a continuation monad, you can write your CPS factorial just as int to cont r int. And if you start writing that function, you quickly realize that this is the only way to write it. And use Haskell and use do notation. And if you write this program, it's automatically tail recursive. And you never have to think about control flow and all this. So the continuation monad is a very powerful abstraction. It takes away this view of thinking of continuations as functions. Instead, you think about writing programs in the continuation monad like this. Okay. Now, if you know the history of continuation passing and CPS, there are different ways of doing CPS. The oldest one, I think, is the Fisher style, where you turn a function a to b into b to r to a to r, which is a continuation transformer. Or then there's the Plotkin style, which is continuation in the second argument, so a to b to r to r. But that's the same as writing a to cont r of b. Okay, and all of these things have been studied very well, and continuations give you classical logic and control operators and all other things. So this was just a brief overview of continuations and the continuation monad, and I'm going to take a step further. So continuation monad, and now I want to go to co-exponentials. So what are these things? So what I want to write is a star as a to r, which is a continuation for a, or if you allow me to call it a handler, it's a handler for a. Okay, and b minus a is a value of b with a handler for a. You could also think of it as a value of b with a hole which has a type. You can only plug in values of type a into b minus a. Okay, and when I write the double arrow, it means I'm writing an arrow from a to cont r of b. So it's a CPS function in the Plotkin style. Okay, so these are the abbreviations I used, and if you allow me to use those abstractions, then this is how you define co-curry and co-uncurry. I wrote it down with the explicit types here. So yeah,
Is R fixed?
yeah, R is fixed here. I have not used any for all anywhere. This whole thing is polymorphic in R. Yeah. So here's the program co-curry in Haskell with the cont monad. Point. So yeah. So f is this function. C comma a to r is c and a continuation for a. And from this, I can produce b to r to r. So K2 is a continuation for b. I run f on c, and then I get something in a plus b. So the key insight is if you have a continuation for a plus b, you can split it into a continuation for a and a continuation for b. Okay. So when you run f on c, you have to plug in two continuations. So when it is a, you call k1. When it is b, you call k2. If you want to write the opposite program, you have a continuation. You're trying to produce c to cont a plus b. So you have a continuation for a plus b. You can inject left and split it into a continuation for A and a continuation for B by injecting left and right. And then you plug in K1 into C, into this pair with C, and K2 remains outside. Okay. So it looks a bit mysterious. A better way to understand this is to look at this isomorphism. So you're taking C to something in the continuation monad of A plus B, but A plus B to R splits as A to R, B to R. Then you apply currying and split that into two more functions. And then you join the continuation for A with C, and the rest of it goes into the continuation monad. Okay, so if you go from left to right, it splits the continuation for A plus B and puts it in two different places. You go from right to left, joins those continuations, gives you an A plus B. Okay. All you need to do this, if you want to implement these programs, all you need is functions and sums. So products, functions, and sums, which any functional language which has any of these things you can implement. Okay. Okay. So I didn't come up with this by writing programs, but there is a nice conceptual way of understanding how all of this works. So if you know about simply typed lambda calculus and Cartesian closed categories, there is a way to use the continuation monad to produce the complete dual, which is the co-Cartesian co-closed category. Okay, so I don't know if anyone would like to hit this, or should I skip?
This is only Cartesian closed category with coproducts?
Yes. Yeah. So if you have a Cartesian closed category with coproducts, you can produce a co-Cartesian co-closed category. This is the special case, but you can generalize this much more using abstract nonsense.
So
yeah.
You started by saying that the original problem you're trying to solve is a processing problem.
Yeah.
It's the right way to view this, that you kind of solve a similar problem by constructing a different category. So you've got I split into values and computations, which is the main trick. So I have more slides explaining all of this, but I can talk about those things if anyone's interested. But I just want to mention that this is not new. People who were doing denotational semantics in the 90s, like domain theory and power domains and all these things, or like relational models of linear logic, these kinds of exponentials show up there, but no one noticed the co-Cartesian co-closed stuff. So I tried to take that and improve the theory and try to generalize it using more modern techniques. So well, we can come back to that if yeah. So what are these co-currying operators? So if you have currying, you get evaluation, which is you have a function a to b and you have a, you can apply by doing curry on ID. You can do uncurry of ID, which is basically pairing, but it produces a higher order function. We never think about uncurry on uneval. If you do the same thing with co-curry, so if you do co-uncurry on ID, so ID is just the identity function on the double arrow, which is the return of the continuation monad. And from B, you can produce A plus B minus A. And co-uneval says from A plus B minus A, you can produce B. Okay. So it's a very, very interesting take on what subtraction means, but it actually does compute. And so the slogan here is that co-eval creates a choice. So from B, it's miraculously producing A and B minus A. And then co-uneval allows you to plug in a handler for A into A plus B and produce a B. If you have looked at the continuations give you law of excluded middle, you can prove using continuations. But this is like a more general version of excluded middle, where you have the B
if the B wasn't there, it would be A plus minus A. Okay, Phil Wadler has this story about how you're making a deal with the devil when you do these kinds of things, and there's also an interesting story here with the B. But, yeah. And if you know about models of differential linear logic, there are these creation annihilation operators, and these are similar to those, but there's no linearity here. It's all just continuations. Yeah.
I'm not sure if I'm missing something, but why are you using minus for this co-exponential operator? It seems like addition and subtraction don't have the same relationship as multiplication and exponentiation.
Different people have used different operators. So Lovier used minus. There's this subtractive logic where people use minus. Sometimes they use slash.
But are we supposed to think of it like an inverse to addition?
I can show you the type isomorphisms it satisfies, and then you see that it's more like a truncated subtraction, not really subtraction. Yeah. But I'm not sold on subtraction, but it's just a convention. It seems to work nicely with these A plus B minus A's. Yeah. And
vertical. A plus B minus A is equal to B, isn't it? Can I take a B and turn it into an A plus B minus A somehow?
yeah. This is what it's doing. Yeah.
Co-evaluation. Yeah, maybe that explains.
Oh, but you put it brackets. Oh, right, so that doesn't matter. It's bracketed differently.
Oh, right. Okay, so that's interesting.
Is that essential or?
Yeah, the bracketing is essential. So you're saying whether
Is A plus B minus A isomorphic to A plus B minus A?
I have to check. There's no abstract reason why they should be the same, because
They won't be the same with the abstract ones.
yeah, but after writing it out explicitly, maybe something happens there. Okay. Yeah, I don't think they are, just from what I've said, but maybe they are. I don't know. Yeah. Now, so currying gives you lambda abstraction, lambda application, and you can use these co-currying combinators and turn them into binding operators. Okay, so I write them as co-lam and co-app, just like lambda and application, but co-lambda and co-application. And since we're working inside a monad, you want to use call by value framework like Moji's computational meta language, and I extend it with these two operators. So this is the kernel language which has these dualities. So you take a call by value lambda calculus, you add some types, you add a star type, which is just there, and for every type there's a star, and you dualize the lambda abstraction and lambda application to this. So lambda produces a function, lambda bar binds a continuation, produces a sum, and application applies A star to A plus B, and this is the bar application. Okay. So the slogan here is binding a value gives you a function, but when you bind the continuation, you get this choice like A plus B. Okay. Now this choice is very interesting. It captures what control flow is, and I'll try to show you this. And the thing is, yeah, okay. So it's call by value. You also have to add equations. So just like you have beta eta equations for call by value, only up to values, you can have beta eta equations for these lambda bar, where instead of values you take continuations, and if the plus is a value, you can have an eta rule, same thing where you do substitution.
Is plus commutative?
Yeah, and
Some of it looks very asymmetric.
yes, it looks yeah, and the fact that plus is commutative is important, and I'll So if you like, since it's called by value, we know how to axiomatize these using Fried categories. So Fried categories have split values and computations. You have Fleisley exponentials, which is this adjunction. And similarly, you can do Fleisley co-exponentials. So you have to add this adjunction.
The plus is just a coproduct, right?
Yes, it's a coproduct in the plus.
Yeah,
Anything that plus has. Yeah. It's just that you have a left adjoint to plus now. Yeah. And yeah, so I can explain this both in the syntax or using Fried categories, and these I have extended Fried categories with closed and co-closed, and I give a definition for them, and they have these axioms, and they completely axiomatize this language. And this is a fine-grained language where you can understand control flow and continuations. It's a language, so you want to think about all these things, and it has very good semantics. And because I've added a binding operator, you have to be careful you haven't, broken substitution. So it has weakening substitution, and it has an operational semantics by translating into CPS. You get a direct style semantics. It has a categorical semantics using Cartesian closed category and a strong monad with or with the Fried categories, and you instantiate this into any Cartesian, let's say, set, and you get an adequate denotational semantics which matches the operational. And further, you can translate it into simply typed lambda calculus with sums, which is conservative over simply typed lambda calculus. So it's all conservative extension. Now, I probably should have mentioned, yeah, so there are other languages for combining functions and continuations. The main difference, so if you know, Hugo, Rebellion, and Kurian, right? Yeah, 1997 or 2000. So mu bar was like the duality of computation, right? So they invented this language where they split values and continuations into two different contexts, and then there were operators similar to call CC to move between the two. But the main difference is here I never split values and computations. Values and continuations. They all live in the same context, and I never allow you to create continuations except only using these co-exponential operators. And similar to the whole program of polarized linear logic also does similar things, but you add polarities to the types, and you have to do all the meta theory has to be done in two different ways for positive and negative types. And yeah, so this is how it compares to the other languages. This is the language which has both exponentials and co-exponential, but okay, these are call by value exponentials and co-exponentials, so they're weak in some way. But more importantly, it's not a degenerate language, and it means you can give a computational interpretation to all these other languages with subtraction, logics with subtraction, like co-intuitionistic logic and subtractive, without going to linear logic. Okay. So this is the and the main trick was literally just split values and computations. Don't do values and continuations, do values and computations. Okay. Right. Okay. So so the fact that this works should make you think why continuations are so magical, right? It's a surprising trick, but once you see the trick, oh wait, it's just continuations. But so this is just a thought. We are working in the Fleisley category of the continuation monad, and we had these co-exponentials, but we screwed over the functions in some way because they became call by value functions, and the products become pre-monoidal products in the Fleisley category. But these are well-known techniques in PL, and what I'm saying is, instead of a programming language, you're getting a call by value programming language. That's it, right? Yeah.
So you keep using the term continuations, right? That was a choice of structure, right? So you're choosing the Fleisley category for conversion one, and then as a property that is Fleisley for Fleisley, that is for Cartesian.
Yeah.
You have other models where you
No,
okay, but you also don't have the free model.
So
right?
So in the free model, I have to explicitly add the star. It's not like it's a specified co-exponential, not yes, right, yeah.
Yeah, so there are many other no-go theorems like this. When you have dualities, it makes me think that this trick could be played somewhere else. I don't know where else. For example, in quantum foundations, these things often occur. And yeah, okay. And the second thing is the fact that we can use continuations to, build this duality between exponential and co-exponential means that they should really have the same status. Like we always think about first order functions, but we always encode continuations as functions. But instead, we shouldn't conflate the two and just think about functions with currying and continuations with co-currying. And just as a bit of propaganda, dualizing things from taking ideas from category theory and finding applications in programming languages is a very fruitful trend. So here's like monads and comonads are very popular. So maybe the next big thing could be exponentials and co-exponentials. And maybe that's a nice way of thinking about continuations. Okay. Now, I will try to convince you that co-exponentials, thinking of continuations using just this interface of co-exponentials is a very powerful idea. So here's co-exponentials in action, just like handlers in action. So you can do lots of things. You can either do this on paper or you can implement it in Haskell and use the continuation monad with two operators, colam and coap. So I'll show you these things by writing programs in Haskell. So first, continuation gives you classical logic, which is the law of excluded middle, but excluded middle is just a special case of this colam operator. So lambda bar x dot x is literally a plus a star. So colam applied to identity gives you excluded middle. Other classical control operators, so call CC. So you can think of colam as also a generalized kind of call CC, and so the type of call CC, if you take this type, this is it's Clavius's law, I think, in logic. So a star to a. You do colam and you get a star plus a star, and then you just go from a plus a to a using codiagonal. So you can derive all the classical control operators using just colam and coap. Right. Okay, and more importantly, having a plus b inside a continuation monad is like having two continuations. Okay, so it's like Tiliki's double-barrel CPS, which Sam told me about. So using that, you can actually write programs which perform backtracking. So here's some combinators which let you do backtracking. So I'm writing this explicitly using continuation monad. So assume right. So you want to produce something in a plus b. You can make a choice. You go left or you go right. But instead of left or right, you choose these operators, which are assume right and assume left. But so assume right says you're allowed to produce a b, but with an environment which has a continuation for the other side. Okay? So a to r, I'll give you a to r, and you have to produce a b, and this produces an a plus b. So that's the intuition for colam. And resolve right is you have this computation that you produced, and it plugs in a continuation for a to r. And that gets spliced into that thing that you assumed. And then these plus is commutative, so plus you can swap. So you can swap the choices you make. And when you combine swapping with these left and right assume resolve, you get the other direction. So what is the essence of backtracking? You want to go. You have two choices for your execution path. You go along one direction, but you realize that something is wrong. So you swap and go back. Or I mean, you go back and swap, and then you go down again. So that's the intuition of these combinators. And so assume left, right, resolve left, right, and And then there's a way to run the whole computation by plugging in the two continuations for A2R and B2R. Okay. So I wrote several programs using it. The biggest program that I wrote is a SAT solver. If maybe I'll quickly just show this demo. Right. So this is a SAT solver which has environments and things, and we are trying to solve this Boolean proposition. So so SAT solver takes an environment and the proposition you're trying to solve, and it has a failure and a success. Okay, so these are the two choices. There's a little bit of hack here with the R, and it tracks the state of the SAT solver. Okay, so this function solve is written entirely using these assume resolve combinators, and just as an example, when you see a 0, you have to fail, and so you assume left and just return. Okay, and if you see a 1, then you assume right and just return this continuation. There's other fun stuff which happens when you have and, so you assume left, giving you success of the rest of the computation. You resolve the P1 using the success, and you keep track of the state of the whole SAT solver inside the result type. So this entire solve function can be written inside lambda star, and then the final SAT solver is actually going to run the continuation by plugging in the thing that produces the output. Okay. There are more interesting programs that you can write, but I wanted to show this one. It's the biggest one that I've written. Huh? Oh, yeah. I will need to. Yeah, I have to write a formula to solve. Okay, but it does run. Okay, I mean it certainly compiles because you can. But you have to call SAT with the formula. Yeah, which is going to take time. But people write SAT solvers in Scheme and all these things using continuations, and you can compare against these because here you have a much. These combinators give you better types, basically, and a way to think about the control flow in a principled way. Okay. The way I've been thinking about. I'm not an expert in imperative programming, but there are many ideas where you have like things like speculative execution, checkpointing, backtracking, and the closest I could think about is to relate this to this idea of speculative execution, which happens in CPUs, which is you want to produce you want to produce something of A plus B, but you can't commit to left or right. So you speculatively choose right, with assume right, but you get a free continuation, and now you may or may not use it to do backtracking or just proceed along B. But someone who runs your program can choose to splice in a continuation for A. So if you ever use the continuation for A, that part of the program gets followed. And the key idea is the system always manages both sides of the execution. And depending on how you run the program, it either uses your computation or jumps up back to a top level continuation. Okay. This is the informal explanation, but the point of having a language with an equational theory is that all of this is algebraic. So this is an algebraic axiomatization of these ideas from imperative programming. And then the next thing is I tried to understand effect handlers using these co-exponential operators. So very naively, effect handlers are you have a signature functor F, and you take the free monad on it, and to use continuations to encode effect handlers, my naive attempt was to just take the church encoding of the free monad, which is there in Haskell. Sam tells me that this is some kind of co-density monad, which Christina knows about, but I don't know. So when you do this, so you have basically two continuations to manage. One is FR to R, which is your handler algebra, and the generator A to R. Okay, and if you instantiate the this colam operator with this polymorphic for all R, plus it has to be F of R instead of a simple type. So there are some tricks around polymorphism and the system of encoding here, but it gives a very conceptual way of understanding the fact that it really is two continuations. And when you do colam free, you are going from free FA to cont R of FR plus A. Okay? And this is colam, which gives you the algebra, the F algebra and generator, and then you just push the handler inside the continuation monad. Okay, and if you do this, then you can write the universal property of the free monad. So so free monad just means algebraically free, which means functor algebras are in bijection with the monad algebra. So if you unfold that, you get this fold function, which is colam free, and then you run the algebra and the generator, and then just call reset 0, which is run cont of ID. Okay, and if you have these three operations, you can do all of effect handlers, which I did. I tried to reproduce Sam's drunken toss example, and here's so fold free, and you need to show that it has the wrap property of the free monad, and then just two operations, fail and choose. So fail has arity 0, choose has arity 2. You can do a toss where you choose a Boolean, and if it's true, then heads or tails. You can do a drunk toss where you do it twice, or you can do it n times. And you can write handlers for them using the fold. You can use different monads to interpret the fail function. And so when you take, when you want to compose handlers, you want to take the sum of two functors. And I know this from Nicholas Wu and Tom Shivers' paper, where they take the sum of two things, and this is how they write it. So I tried to do it like this, but again, all of this can be derived using just the fold of the free monad. And so different handlers, and here are some of the examples, which are there in Sam's slides, and they actually run. And yeah, so there's a way to recover the CPS encoding of effect handlers, I believe, using this understanding. I'm not sure if it matches the same thing that you guys are doing, but yeah, we can try to. The first thing is, if you have functions and continuations, we've been thinking about functions, but if I give you continuations, can you get back functions? Okay, there are many ways of doing it. And the thing that I really like is this idea of functional completeness, which is due to Lambic and Scott. And if you have a Cartesian closed category, you can, you are allowed to bind a free variable and then keep writing programs. If you think of the dual of functional completeness, then to prove A plus B, it is sufficient to prove B, assuming a continuation for A. And this entire concept of functional completeness for lambda calculus can be dualized, and you can do it using category theory and so on. And from functional completeness, I use this is a less known paper of Hasegawa, where he splits lambda calculus into kappa and zeta, which is, and he produces these first order arrow languages where you have these binding operations called kappa and lift, and zeta and pass. So kappa doesn't have function, and zeta only has functions. Okay, this follows from functional completeness. If you dualize, you can produce kappa star and zeta star, and I did that. And this is a language which it doesn't have functions, but it has backtracking and control flow.
And it's a very mysterious language because you have like, if you add natural numbers to it, you get a first order language which has primitive recursion. So it's not as powerful as system T, and it's more powerful than a first order arrow language. And then you would try to study the expressive power of this language. I don't have a good answer for it yet, but I tried to think a little bit about this, the generic count effect, effective count paper from Daniel and Sam and John Longley. Okay, right. Here are some fun programs that you can write in kappa star and zeta star using arrows. You can split the program A to A, the identity function, into these 4 steps in 2 different ways. It looks like snake equations, and these operators give you like code pointers into the execution of the program. And you can, for example, you have a sequential program, but if I give you a free continuation, you can use zeta star to splice it in, and then between z plus c and z plus d, you can write a new program which may or may not use the z. And it seems to me that these ideas could be related to things like checkpoints and breakpoints and debugging. I'm not sure about the formal details yet. There are type isomorphisms of these subtraction things. So x minus 0 is x, 0 minus x is 0. So that makes it like a truncated subtraction. X plus y minus z is x minus z plus y minus z. It also interacts with functions. They look very funny. Another thing is, so what about the type A minus A? The type A minus A is not 0, but so Lovier thought about these things a long time ago, and he called it the boundary operator. So the boundary operator has a Leibniz rule, and there could be some connection between, differential things in programming languages and this del operator, which is A minus A. There's a connection with session types, which is how I initially started thinking about them. In session types, there are 2 kinds of functions. One is A star par B, and other is A tensor B star. And when you do programming in CP, you do cut, which is the composition forwards. But you can also dualize this, and you get a program in session types, which does exactly this. So that's another thread. Co-exponentials, different people have invented them, but no one identified the universal property. So I went through a lot of literature on continuations and CPS languages, and here are some places where they do appear. But okay, and I will conclude here because there's no time. So the main thing is that there is a deep duality between functions and continuations if you take the point of view of category theory. And they do have a very nice computational interpretation, and you can reinvent a lot of the theory of continuations in a very algebraic way. And the third point I wanted to make is that to understand computation, we want to understand functions, right? And linear logic gives you all this, tensor products and linear things. And Girard wanted to decompose the function space and, using the bang, which is the resource interpretation, or A star par B, which is the producer-consumer view. If you use continuations, you do get this decomposition A star plus B. And then there's the other way of decomposing, which is also interesting, which is the D of A to T of B, where D is a Girardian comonad and T is a Moji monad. And so different ways of, so I see it like in the spectrum of linearity, monads, comonads, and exponentials, co-exponentials. So, yeah.